All right, welcome back to our session. Hopefully you got a chance to view that video, and you should also have seen in that video, again, the steps that they went through from taking a sample of a particular size and, importantly, building up this idea of a sampling distribution. The idea that if you were able to take every single possible sample of that same sample size and calculate the sample mean for each one of those samples, and then generate a frequency distribution, if you will, or a probability distribution for all of those sample means. What exactly would that sample mean look like? And we saw they discussed what the average of that sample, that distribution of sample means would look like, and what the spread of that distribution of sample means would look like. And of course, it's that distribution of the sample means that we're referring to as the sampling distribution. And one important note is that whatever parameter you're interested in estimating, we very often will estimate the mean of a particular population. But we might want to estimate the spread. We might want to estimate the population standard deviation, or the proportion of a population that meets a certain criteria. Whatever population parameter you're interested in, you can generate or imagine at least a sampling distribution of all the possible sample statistics that you could come up with by measuring, say, the sample standard deviation for every possible sample, or the sample proportion for every possible sample. So a sampling distribution exists for every sample statistic that you could measure on a sample. And those sampling distributions will have specific characteristics. They'll have a specific mean, a specific standard deviation. But as we saw, if we know enough about any distribution, if we know the mean and we know the standard deviation, and we know at least something about the shape, we can say some very, very important things about the probability of a specific value falling in a particular range in that entire distribution. And that really is the idea that we're going to use as we go into inferential statistics. So the video went over this and they took you through that process. I want to step through a little bit more detail and kind of show you in an example that will actually work in Excel, kind of what a sampling distribution might look like and what are some of the things that come out of a sampling distribution. So let's back up first though and talk about some methods for random probability sampling. Simple random sampling, systematic sampling, and stratified random sampling. And all of these in some way involve random sampling, but as we talked about earlier in the course, our main idea, the reason we're trying to go after randomness, is that our goal with a sample always is to strive to make it as representative of the population as we can. One way to do that, again, is to just try to be completely random in our approach, not introduce any bias in our approach to selecting members of the sample. But depending on your specific situation, there are things that you can do to maybe help make sure you're sampling from across the entire range of the distribution of the population. And a few of these slightly more sophisticated approaches attempt to do that. And there are many other ways you could go about this depending on your specific situation. But let me just highlight a few of these that the textbook goes into. Simple random sampling is really the simplest method, and the idea here is to give every member of the population an equal chance of being selected. And you could imagine ways, for example, if you had imagine a spreadsheet where you had a list of values and you wanted to take a simple random sample from that. You probably could imagine, and I'll leave this as an exercise for you, to imagine how you could use the random number generator in order to pull out from a list of values in a column, let's say, of data in a spreadsheet, to pull out a random sample from that list. Okay? You could imagine generating a second column of random numbers beside that first column of data. What could you do with those two columns of data in order to pull out a selection, a sample from that original list that you know is random, based on the fact that your random numbers are random? I'll give you the opportunity to think about that. I won't give you the answer here. It's a fairly simple thing, and if you can ask me questions when we meet together in class if you want to see how that's done. Again, it's quite simple. But the idea, just use the randomness of the random number generator to select a random sample. Okay? Sort of the eeny, meeny, miny, mo method, as kids used to say. Okay, so that's just simple random sampling. So we can use random numbers to aid in this selection in some way. Very similar to the video where they were drawing names out of a box. Another method that is just slightly more sophisticated is called systematic sampling. And the idea here is that we're going to add a little bit more of a systematic view to picking this sample. And it works really well in situations where the observer and the population are passing by each other. So we pick some fixed point, a beginning point of taking our sample, and then we determine an interval. And then we pick every nth item, whatever that interval is, n. We pick every nth item after that first spot. So I might pick the first item, and then I decide my interval is 10. So every 10th item after that, I'm going to select. You might imagine if you're interested in understanding the range of car models that are very popular in Winter Park. You could stand out on the corner of Park Avenue and Fairbanks, and you could look at the cars that are going by. And if there's a lot of traffic, it might be very hard for you to write down every single model of every car that's going by. But you might say, hey, let me pick a random sample. I'll look up every 10 seconds. And their car that's in front of me, that's the one I'll write down. So you pick some fixed interval, or maybe every 10th car or 20th car, instead of trying to write down every single one. So that's one good example. Another example is in like an assembly line, where you may just, at random, you may select every 10th item that's coming out and inspect that in more detail for quality control. So that works fairly well in a lot of similar situations. It's often very easy to implement and can be very useful. One of the things, though, that you have to be extremely careful about, you have to apply a little bit of thought when you're using this methodology, because if you're not careful, you can introduce some unintentional error if you select a poor interval. And perhaps you can think about some examples where that could be the case. I'll give you one to ponder. Imagine you're trying to get some information about traffic through a supermarket. So you decide you're going to take some information from one of their main stores at various times over the course of a year. You're going to go in once a week or some period of time, and you're going to sit down and you're going to grab a snapshot of what the traffic is like coming in the door at a certain hour of the day. And the store is open every day. You're trying to capture some sample of what their daily traffic would be. Well, you might find as you're selecting an interval for doing this, that an interval of 7 days may not be a good time to do this if you want to get a good random sample. Because if the store is open 7 days a week, you may end up going in on a Tuesday the first time, and then if you say, well, I'll pick 7 as my interval, come back 7 days later, well, I happen to be on a Tuesday again. And if I come back 7 days later, you see the pattern. We end up only getting a picture of what's happening on Tuesdays. And maybe the traffic on a Tuesday is very different from the traffic on other days of the week. So in that case, anything other than 7 is probably a good idea. So over time, you'll get samples from all the different days of the week. So you have to apply a little bit of forethought as you select the interval that you're going to use when you do systematic sampling. But otherwise, it's one that's implemented very broadly in a lot of different applications. The third one that the text goes into is called stratified random sampling. And it's actually a way of enforcing a selection of your sample from across the entire range of a distribution. One of the things we'll talk about is sampling error, just the mere fact that we're not observing and recording every single member of a population means that there's a chance we may miss some portion of the distribution. And even though we're using random sampling, just the sheer luck of random numbers, some of which is good and some of which is bad, may cause us to miss certain parts of the distribution. So what stratified random sampling does is it takes the entire distribution and breaks it up into segments. And then within each segment, we randomly sample again, just within that segment, and we can be very careful to try to maintain the proportion of our sample that comes from each segment if we know some idea about what the shape of the overall population distribution might be, or if there's some way of gauging that. So, for example, if you're interested in getting some information about income levels across some community, you could decide to break up the community by educational level, stratify by education level, and say, okay, I'm going to take a sample of a certain size among people who have had up to high school education. And then I'll take a sample of another size, a random sample within the group of people that have had some college education. And then another random sample within people in a different education strata. So in that way, we can imagine that we're breaking up the entire distribution. We're forcing ourselves to make sure we're not missing any of those segments by, again, enforcing this sampling from each segment. And if we take pay some attention to the relative sample sizes, we can, in a way, do a fairly good job of making sure we're sampling proportionally from across the entire distribution. And if you like, again, you can stratify based on more than one variable. In a way, it's sort of like our idea when we introduced pivot tables, that we're breaking our entire distribution down into clusters and then sampling within each of those clusters just to make sure we've covered the entire distribution of the population as best we can. So these are three different methods that are applied to sampling. The idea overall being to do whatever we can that makes sense in our situation to get the sample to be as representative of the entire population as possible. Even when we do that, though, there are some sources of error. There are some things that can go wrong. Just the fact that we are not recording, as I said, every single member of the population does inherently introduce some error. And there are two basic sources of error. One, which is what we call sampling error, which is error that, again, just comes from the fact that we're looking at a sample and not the entire population. And the way to get around sampling error is to increase the sample size. Imagine if we had some kind of a distribution in a population and we were just taking a sample of size 2. 2 members out of that population. Well, those 2 members could have the same value for whatever parameter we're looking at. The video you saw talked about height. Suppose I picked 2 people who had about the same height. Well, that sample doesn't give me a lot of information about the entire distribution. Even if those 2 people were some distance apart in their height, there still is not a whole lot of information captured. But the more and more members of my sample I have, the more chances I have of selecting from across the entire distribution. So the way to reduce sampling error is to increase sample size. Essentially, all the way up to my sample size being exactly equal to my population size, in which case I've totally eliminated sampling error because I'm not really sampling anymore. I'm looking at my entire population. The other source of error is really the catch-all for everything else. It's non-sampling error. It's everything else that can go wrong when you try to make a measurement and do estimation about a population. So it can be caused, as the slide says, by poor measurement, by poor choice of sample, by poor choice of interval if you were doing systematic sampling. All these things that you can possibly do wrong in your measurement and in your selection of your sample. All of these can come into non-sampling error. And here, larger sample size does not help you. More and more of a bad thing, unfortunately, does not become a good thing. So what are the kinds of things we need to look out for specifically in non-sampling error? Well, measurement error. Okay, we could be taking measurement on our test equipment or measurement equipment, could be out of calibration. We could make typos while we're recording the data in our spreadsheet. We could be capturing information on income levels across the community, to follow up on that example. And someone may tell us in the interview that they make $28,000 a year, and we write down $82,000 a year. Just a simple typo, little dyslexia of the pen. And we end up skewing our data significantly if we've introduced a number that's very far off. So all of these things can be sources of non-sampling error that are measurement error or recording error. Selection bias is another source of non-sampling error, and this comes out of a flawed sampling plan, some way that we're not capturing our entire population, across our entire distribution of our population. A famous example of this was an election way back. I think it was 32. Was it Landon versus Roosevelt? And there was a big literary magazine up in the Northeast that did a survey of their readership, because they said, hey, people should really get an idea as to who's going to win this upcoming election. And they did a detailed survey. They went out and they looked at their readership base, and they said, how do we get a good sample of our readers, our subscribers? And they did as a good job they could of crafting a survey, good survey questions. They went out and did the best job they could of recording the data accurately. And they came back and they predicted that Landon was going to win by a landslide. And as it turned out, of course, things didn't go that way at all. And when people look back at it, well, what was the problem? Well, their sampling plan was the problem. What was happening in that era? Well, we were just in the throes of the Depression. So anybody who could subscribe to an upscale literary magazine, they were not really representative of what was going on in the entire country at the time. So among their readership, there was a tremendous amount of support for Landon, but that didn't really reflect what was going on in the entire country. A third source of non-sampling error that we need to pay attention to, and it's one that comes up a lot when you're dealing with market research, is something called non-response error. And it's where a segment of the sample is not included, not necessarily because they weren't in our sampling plan like that literary magazine, we just didn't sample from the entire distribution, but for some other reason, a group, a specific segment of the distribution of the population does not respond to our survey, for example. And as a result, the responses we do get tend to be skewed because they're not representing the entire distribution. An example that comes to mind is the west side of town is going through a tremendous growth, right? West Orange County. Tremendous growth in the last several years before all growth came to a stop in 2008. But supposing you were working on developing a major entertainment complex over there. And you said, okay, people have reasonably good disposable income here, but if people are going to spend a lot of time on entertainment, well, I need to know what kind of disposable time people have. I need to know how much free time do people have. A lot of times people might be working extra, working long hours and 2 jobs and things like that just to try to keep up. So let me get a sense for what kind of disposable time people have. So I'm going to create a survey, and I'm going to ask people things about their leisure time to get an idea as to whether or not people are going to have the kind of time to come into this entertainment complex and obviously spend money and generate revenue. That sounds like a good thing to do, good kinds of questions to ask. Well, you can go out and design this survey. Again, you can do like the folks at the literary magazine in the Northeast, and you can design this great survey and select a good sample, and you decide while you're at it, this is a really, kind of upscale, affluent group. I could get some good information out of this survey while I'm sending them this questionnaire. So you make it pretty elaborate. You go out and you end up with about 8 pages worth of questions, and you figure if I get the answers to all of this, I could sell this data to people. This could be really important information to have. So you ask a whole lot of really, really good questions. You end up with like this, 5 to 8 page questionnaire that people have to sit down and fill in, and you send this out to your entire group. And if it's like most mail order campaigns, you get like what, a 4%, 5% response maybe across the entire population. That's fine. But out of the entire group that you're trying to sample, who are the ones that are most likely to have just taken your survey and thrown it in the trash? Well, out of the entire distribution of the thing you're interested in measuring, which is people's available disposable time, the people who have the least amount of time are going to just toss it in the trash. They're not going to take the time to fill that out. So more of your responses are going to come from people who have more time. It's like, hey, I've got nothing to do. I fill out this 8-page questionnaire. And what you've done is you've introduced non-response error, because a segment, one end of your distribution, tends to have a higher propensity to not respond than others. So your results are going to be skewed. You're going to get back whatever size response you get, but it's going to show you a skew towards one end of the distribution because unfortunately something in your survey design made it less attractive to one portion, one end of that distribution to respond. So these are a variety of things that we have to be careful about when we're doing sampling to avoid these various types of non-sampling error. And as far as sampling error is concerned, the key is to make sure our sample size is large enough. And if you'll recall from the video, and if you haven't watched it yet, this would be a good time to go back and take a look. But if you recall from the video, the key is that the sample size that's needed is based not on the population size, but it's based on how accurate a measurement do we need. How accurately do we need to know the data? And that's something else that's important for us to pay attention to. So, we've talked about selecting samples. Our next segment is going to take a look at an introduction to estimation. We'll assume we've been able to go out and get samples of a certain size from a population that are good representative samples, and we're going to take a look at what does it mean to have a sampling distribution. So we'll pick up on that and see how that builds into estimation.